Okay, so we are live. All right, so to pick up off where we left off before, I believe I was going into the terminologies for the paper for SSD, um, but yeah, the internet dropped around here. So yeah, we can start off by discussing about the important terminologies that we will go into the paper with. I won't be discussing too much about the paper because do want to get into um, more important concepts of CNN, which it seems like I missed while discussing just regular deep neural nets. Okay, so I was discussing about mean average precision. Um, the reason I believe precision was used as the measurement of performance for object detection in the paper is because that it gives a better look at performance of object detection rather than just accuracy. But I still don't think it's the best look at how well a object detection um, algorithm is doing its job. The reason is this: you can see this here. So this is a I suppose that both these for bounding boxes are detecting, say, cat. Then the precision is measured by this blue area here divided by the blue area plus the yellow area, right? And so this is about like 80, 70 something precision. The main average precision would be the average of precision for these bounding boxes. So 70 something is not bad. Um, okay. But the a caveat with measuring this way is that something like this, because there isn't false positive in here, there's only true positive and the false negative, the things that hasn't been detected. This is actually 100% precision. So this is fine. It's fine under certain situations if you don't really care about how large your box is. If you're really just trying to have an approximation of where an object might be with your bounding box, that is perfectly fine. But if you do need to know about the size, about estimates how close it is and stuff like that, maybe you're saying like if you're driving a car or something, then um, this may not be 100% precision might not be good enough. So I'm going to argue is that a better measurement here would be like using IOU, which is intersect over union. So this will be the intersect, and the union would be the whole thing. Of course, assuming this is the property, it's capturing the same element as the red bounding box with the ground truth. And this will be the green area divided by green area plus the white area inside of here. And you can see this is not very high intersection or union if you measure that way. The L1 loss indicates difference between the bounding box points. So this is actually pretty large L1 loss. You can see that there's difference between these four coordinates here, and the it said that the in the paper that the algorithm takes to minimize the L1 loss. Let's go to the good browser. I'm just gonna go back here. It's fine. And so one thing I'm gonna say that I do know people don't really attend the webinars on time, but I do hope it's able to help um, people at grasping, just getting more knowledge and understanding. And you know, maybe just open an area of interest where you are exploring. So yeah, so single shot detection. So I just give a general idea of how, like, what it does. So in single shot detection, there are proposed, let's say, these default boxes, right? And these are used to approximate these ground truths. Of course, they are. So you have these boxes and how far they're off from, like, well, yeah, how far this one is off from here, how far the cat is off from one of these. Well, you do each and every one of them, and of course not all of them are going to be used. Okay. So what this does is that it uses a feed-forward convolution, and each one of these convolution you can see. Well, you can't see. I have a hard time seeing here. Um, that it actually is trying to give the class and predict the class in plus 4, which essentially is how far off your 4 coordinates are from the ground truths, and each one of these are in different. They're in, let's say, different scale and resolution, and they add some. They add up together, and you'll be able to apply non-maximal suppression at the end of it. This is said to have done a better job than YOLO and other recurrent networks like region proposal networks like Foster RNN. Actually, no, RCNN. Yeah, but there's one thing you will notice recently is that even for YOLO, a lot of them will look similar to this. Of course, it's not using the same technique; it's using the residual network, but this is a good concept like that. Okay, so see the training. It is training default box. That's one true. So the training objective is to reduce the L1 loss here. Okay. Um, but yeah, anyway, I'm not going to stay on too long for on this paper. So one thing you can do for this is that instead of using MPA as a measurement, you could use IOU as a measurement of performance. There's no doubt that this is better than the existing YOLO architecture, but I like um, better, more subjective, well, less subjective measurement personally. All right, so onto CNNs and how they work. All right, so the motivation behind CNN is that you can see things like here. This is both these images here is a cat. This is taken from the Udacity lesson notes. So both of these are cats, but if you are having perceptron or something that does not take into consideration, what you say, spatial information, it'll be very hard for them to learn that this is the same as this cat. It'll take a lot of work, and you'll see this is this example being executed late. Well, I wouldn't really execute because my computer really slow, but you'll see an example of this later on. This I will be executing this with the MNIST. So the idea is that the way um, you can essentially say that this kitten is the same as this kitten is by the way of doing this is by weight sharing, right? Because as you know, right, as you know that every time every convolution layer there is a lot of convolutions, and essentially these are filters. And if you share the weights of the filters and they get convolved the same way, then it makes sense that this and this would both be classified or gather the same information, that they would be active for cat. Right? It will see that this is similar here. So this is also similar in the natural language model. Of course, we're not natural language model is not covered by this course, but you can just imagine the idea of it. Let me run that again so it looks nice. Cool. All right. So for better understanding, you always look at this Stack Overflow and how it works. That's how I got a better understanding of this. Essentially, it in essence applied to entire image, same weights. Yeah, patterns with filler. It's a little more complicated than that if you really want to dig in, but this is a good start idea. And okay, so I won't be talking about exactly how you do the padding, same padding, dropout, pooling, all that stuff, because it's covered pretty well in the lesson notes. But I do find that the material cover for convolution was not sufficient for me to understand how convolution really works. So I'll briefly go over that and suggest some additional resources that you can look at if you want even more understanding. Okay, so you can see this is a 32 by 32 by 3 image, and this a 5 by 5 by 3 filter is applied onto this. Of course, this is going to be valid padding because you can see it's being reduced down to 28, and this is it's given back a 1 by 28 by 28, right? Everything, every convolution, every filter, let's see, every 5 by 5 by 3 filter results in a scalar, so it flattens down to like this, right? And if you do that 6 times, right, you get 22 by 20, 28 by 28 by 6, right? So you have 6 activation maps here, like that. And yeah, and actually, as part of your project for project 3, you are encouraged to take a sneak peek at one of these filters. It comes out pretty interesting. Like it's actually it tries to capture edges and all sort of stuff like that. Okay, and so an idea about the fully connected layer. So fully connected layer is what follows the convolutions. Basic is the result of the last convolution layer. It gets flattened, and so it gets feed into the neural network, similar to like what you did with which was done with MNIST. But now there's like a lot of instead of taking just the flat image, you have you're taking a lot of convolution and filters, and you collect a lot more information, more useful information at that, right? Okay. And onto project 3. A brief discussion about what you might do in the project. There's something you have to worry about. You are given a workspace. I believe you do have a limited amount of GPU usage. What's recommended is that you turn on your GPU when you need to, when you feel that you have a good model built out and you're just trying to tune your hyperparameters to things like learning number epochs, and potentially adding a new layer and stuff like that. This is just in order to save GPU. I would at least recommend that you run through your stuff one time with your CPU to make sure everything works. Because every minute of your GPU is precious, and if you do run out, you could always request for more GPU time. I had done this for my computer vision project. At one point, somehow the cloud kept running and it ran out GPU, but I requested some more and everything was fine. So that is always an option, but try to be prudent with GPU usage. Um, okay, so to go into the project 3, so your task is to classify 32 different traffic signs. If I remember that correctly. Your one of the challenge is that you are trying to beat the state of the art. That of course this 97% believe is for the competition that have a lot more labels, but nonetheless, we're trying to do better than Facebook's Yan Kun, which is a feel good moment. For this project, you are expected to use TensorFlow, right? Okay, so I'm not going to go in details of the project, but let's see how you can do some of the basic stuff with TensorFlow, and this is done using the example of MNIST. Right. So you already know about the MNIST example with MNIST, but you can see there's some difference here. Instead of reshaping the x as like flattened out 784, we're reshaping it as the 28 by 20 by 1, which is black and white, and however many images there are. Okay, so there's this actually I've taken this from somewhere from the web. But of course, just for convenience, you can see this is a convolution 2D layer, max pooling, another convolution, max pooling. So this is a lot of filter being applied. This is 32 filter, which you can see, from this concept, you can see how that is happening there. 64, and this is following a flattened one. So this is 2 layers with a lot of filters. And then there is a dense, making it fully connected. And there's a dropout, and there's another dense. Yeah, so there is a few dense layers there, making a few fully connected layers. So this is similar to what you can think of like the hidden layer and out layer from the original, what should I say? From the original and this example, but of course, this is following a bunch of convolutions, right? And of course, the same learning algorithm here, reduce main, cross entropy, and something to note. So this took about I run this for about 30 epochs. This is reporting like from 0 to 10. Like it's reporting them wrong. This is actually 10 epochs. This is 20. This is 30. But you can see in 30 epochs, it's already doing better than 90 epochs in just using fully connected layers of a subconvolution. It's a lot more powerful. It can do it recognizes a lot more concepts, and it's able to classify handwritten digits much better. Um, Something to appreciate is that all the handwritten digits are cleaned. You don't see, a smidge here and there, and all that does take work. Something to note, and actually, this is I think some time to just add this example at the bottom. This is I've seen a few students having issue with this, so there's something to note about TensorFlow is that you must have your model defined before you can restore your weights and essentially before you can restore your model. So this is the graph for the flat, actually not really flat, but just the non-convolutional deep neural net for in this example. And this was done somewhere at the top. I still have the pickle file here locally. So what I did was here I reset the graph, redefined everything. I probably don't really need a learning rate, but you get the idea. So everything here is redefined, and then I restore it, and I'm able to use it. I can do a quick run, loads everything, and it's able to use it. So this is something to note. It will might save you some time trying to figure out what's going on once your kernel is taken. Once you stop your kernel and you start trying to restore your model, and suddenly it's not no longer is it's no longer accurate. It's probably what's going on. So yeah, I think that's all the important stuff I wanted to discuss today. I will be sharing this note notebook and all of its resources with you guys on the Slack channel. Of course, you can't use these code directly in your project and work. Yeah, so that'll be that. Thanks for